Today we're going to look at more uses for trig inverse functions. So today we're going to evaluate functions like, or problems like this, where we have to find the exact value of a composition of two functions together. One of them will be a normal trig function and one of them will be an inverse. So first what we're going to do is we're going to work our way from inside out. So we're going to evaluate this inverse tangent, take its result, and evaluate the sine at that measure. So let's take a look at this. So for the inverse tangent, remember the inverse tangent means that the tangent of theta is equal to 1/2. Now to figure out where theta is, we have to consider, well, what values can we get for the tangent? We know that the tangent gives us angle measures in quadrants 1 or quadrant 4, right? Now because this measure here is positive, we know that all the values that are positive yield angles that are in quadrant 1. So this theta is going to be in quadrant 1. So let's go ahead and draw a triangle so that we can evaluate this. Now the reason why we have to draw a triangle is because this 1/2 is not a value that we know for the tangent. So here's theta. Now the tangent of theta is 1/2. Remember that this is the opposite side over the adjacent side, or y over x. So we can say the opposite side is 1, the adjacent side is 2, and we need to figure out the hypotenuse. Now the reason why we need the hypotenuse is because we're trying to evaluate the sine. Remember that the sine of theta is equal to the opposite over the hypotenuse. So we have the opposite side, we need the hypotenuse. So let's do some the Pythagorean theorem to figure out this measure. So we have c squared equals 1 squared plus 2 squared. So c squared equals 1 plus 4. C squared equals 5. So we take the square root of both sides and we get that c is equal to the square root of 5. So the measure of the hypotenuse is the square root of 5. So if we now evaluate the sine of theta, we get the opposite side, which is 1, over the hypotenuse, which is the square root of 5. Now when we evaluate these, typically we don't like to have a radical in our denominator, so we're going to rationalize by multiplying the numerator and denominator by the square root of 5. So 1 times the square root of 5 is the square root of 5. Square root of 5 times the square root of 5 is just 5. Now, this measure is going to be positive because theta, right? Theta is an angle in quadrant 1. We know theta is in quadrant 1. So that means that this is positive, right? Because in quadrant 1, the sine is positive. So this is our value. Alright, so for our next example, we are going to try and find the exact value of the cosine of the inverse sine of -1/3. Alright, so again, we're going to work our way inside out. So we're going to deal with this inverse sine first, and then take its value, its angle measure that we get, and evaluate the cosine at it. So remember, inverse sine means the sine of some angle is equal to -1/3. We're trying to figure out, well, what is this angle measure? Because this is negative, right? Because this right here is negative, that tells us this value is in quadrant 4. That value is in quadrant 4. So let's go ahead and draw a triangle here in quadrant 4. Quadrant 4 triangle. Oh, that's bad. Sorry, guys. Okay, there we go. This is a triangle. So we have theta here. Remember when we're talking about the sine, let me get rid of this. So we're talking about the sine. The sine is the opposite side over the hypotenuse. So we know the opposite side, we know the hypotenuse. This is 1, the hypotenuse is 3. And so now we need to ask ourselves, well, what are we looking for? Well, in the end, we're looking for the cosine. So for the cosine, right, the cosine of theta, we need the adjacent side divided by the hypotenuse. We have the hypotenuse, but we don't have the adjacent side. We don't know what this is. So let's solve for the adjacent side using Pythagorean theorem. So we can say a squared plus 1 squared equals 3 squared. This is a squared plus 1 equals 9. Subtract your 1, we have a squared equals 8. Take the square root of both sides, we get a equals the square root of 8. But we want this in simplest radical form, so in simplest radical form this is 2 rad 2. So this measure here is 2 rad 2. So that's the length of this longer leg here. So let's evaluate the cosine. So we want to know what is the cosine of theta. Well, the cosine of theta is going to be the adjacent side, which is 2 rad 2, divided by the measure of the hypotenuse, which is 3. Then we have to ask ourselves, is this positive or negative? Now, if we remember back to when we talked about where the functions, just the function itself, not the inverse, is positive, we used this little acronym, right? All students take calculus. We use this to help us, ASTC. Well, in quadrant 4 where we are, it says the C, or cosine, is positive. So cosine is positive because theta is in quadrant 4, right? So this is positive. That's positive because we're in quadrant 4 and that's what the cosine is. So this is our solution. Alright, so for our next example, this one's a little different because now we don't have an inverse value inside of the function. We actually have the actual value and then we're taking its inverse. So that tells us, as a result, we're going to end up with an angle measure for our answer rather than a value on the unit circle. So first we have to ask ourselves, what is the sine of pi over 2? We still work our way inside out. So what is the sine of pi over 2? So pi over 2, that's this angle here, right? We have this here, we have the ordered pairs of 0, 1. Now when we're talking about the sine, remember the sine is the y-coordinate. The y-coordinate. So the sine is positive 1. So the sine at pi over 2 is 1. So now this is no longer what we're looking for. We're looking for the inverse tangent of 1. So we're trying to solve this, right? Inverse tangent of 1 is equal to some angle measure. Well, remember, this really means, right? This really means that when we evaluate the tangent at some angle, we get a value of 1. We get a value of 1. Now we ask ourselves, well, where does that happen? What angle measure makes that true? So the tangent, remember, is the y-coordinate divided by the x-coordinate. It's the y-coordinate divided by the x-coordinate on the unit circle. So that means that these two values are going to have to be positive. Exactly the same. Now, we also know that they're going to have to both be positive or both be negative because our tangent is positive. But we have to, again, remember that we restrict the value of the inverse, right? The inverse tangent gives us angles in quadrants 1 or quadrants 4. Quadrants 1 or 4. Now, because this measure is positive, we know that that's going to be in quadrant 1. So we're looking here in quadrant 1, and we have y divided by x. The ratio of this has to be 1. Now, if we think back or look at our unit circle, we can see that if we look here at this angle, pi over 4, it has ordered pairs of the square root of 2 over 2, square root of 2 over 2. If we take this ratio, right, square root of 2 over 2 divided by the square root of 2 over 2, we in fact get 1, which tells us that x has to equal pi over 4. X is pi over 4. Because our angle is in quadrant 1, and its tangent, the ratio of the y to the x, has to be 1. In our previous couple lessons, we were using the inverse sine, inverse cosine, and inverse tangent quite a bit. And we know from those lessons that inverse sine is restricted to values in quadrants 1 and 4, cosine for 1 and 2, and inverse tangent for 1 and 4. Today we're going to look at adding in inverse cosecant, inverse secant, and inverse cotangent. Now, the reciprocal functions are all defined in the same quadrants as their reciprocals for their inverse, except for the cotangent. The cotangent, its inverse, is restricted to values in quadrants 1 and 2 rather than in quadrants 1 and 4. Because if you think about the cotangent function's graph, right, the graph of the cotangent function, it has its first cycle from 0 to pi. And so that's why we use quadrants 1 and 2 when talking about the cotangent function. It is the only one whose inverse is defined in different quadrants than its reciprocal, which is the tangent. All the others are the same. So let's take a look at one of the inverse trig functions that we were just looking at. So we'll take a look at the inverse cosecant. The inverse cosecant is the reciprocal of the inverse sine function. So when we're trying to evaluate this, we're actually going to use inverse sine to evaluate this. We're going to say inverse sine of the reciprocal of 2, which is 1/2. And we need to figure out, well, where is this true? Before we can do that, we have to first figure out, well, what quadrants is this defined in? Now, the inverse cosecant is going to be defined in the same quadrants as the inverse sine. Remember, it's only cotangent that has a different, it's defined in different quadrants than its reciprocal function. So because this value is positive, because it's a positive 2 here, that tells us that we're going to be in quadrant 1. Okay? So remember, the inverse sine of 1/2. What does this really mean? This means that if we take the sine of some angle theta, we should get 1/2. So we're looking for an angle theta in quadrant 1 whose measure is 1/2 for the sine value, right? So if we look at your unit circle, you would see that this occurs at theta equaling pi over 6. So when theta is pi over 6, right, or 30 degrees, the sine is 1/2 because it has ordered pairs, square root of 3 over 2, 1/2. So 1/2 is the y-coordinate, which is the sine. So we want to rewrite this saying cosecant, right? So the inverse cosecant of 2 is this angle here, pi over 6. So this is our solution.